6. We're still going strong. I think that makes next week 7. I think that makes this Monday, Saturday, Sunday, on the 3rd day from now, in the afternoon, during the lab session, our first exam. Okay? Not okay? We're good? Fine. Yay! Yippee! Exams. I'll be in the exam. I'll be in the lab. The topic for the exam, surprisingly enough, is exactly the topics we've been talking about for the past 6 weeks. So yeah, asking about concepts of system classification, asking about concepts of a system that involves electronics, and specifically the components of batteries, wires, resistors, a little bit about diodes, a very little bit about operational amplifiers, which we've seen twice now in lab. And then a whole bunch of concepts of how systems work. The way that systems work for electricity, of course, is V equals IR. That is our equation that allows us to analyze how these systems work. And then we got all these lovely vocabulary words. Good day, sir. From Chapter 1 and Chapter 2. From the suggested text. Again, you don't need to read the book, but that's where we're getting this information from. Most definitely, all these words are defined and talked about inside the prezzies that are linked to our course. So hopefully, there's no surprise. Any killer questions about our exam on Monday? You feeling okay about the exam on Monday? Should you feel okay about the exam on Monday?
Yeah.
I got 2 answers. I got sure, why the hell not? And I got no, I shouldn't feel okay. You should feel fantastically okay about the exam on Monday. It's just talking about exactly the stuff that we've talked about. The goal of this course is not to talk about a whole bunch of stuff for 6 weeks and then give you an exam on different stuff. That's not very useful. The goal of this course is to talk about stuff for 6 weeks and then give you a very boring exam on the stuff we talked about. The question is, how many perfect scores will there be? And then we move on. We keep on going. So the goal is to get it perfect, not to pass. That's not the goal. The goal is to go above the bar. And I haven't had a full perfect class yet, but I'm feeling good this semester. I have no problem with perfect scores across the board. As you guys know, the stuff that we're talking about, I hope you don't find each individual piece or part extremely complex. We could make it complex. And yeah, as soon as you start talking about chemistry, you can talk about the physics of it. We're not talking about amazingly complex things. What makes it sort of new, unless you've already known everything we've already talked about, which is cool too, is that we're talking about going sideways. We're integrating. We're integrating among many little tiny parts. And sometimes folks don't see those individual parts be put together into an integrated system, and maybe thinking this way is sort of new. If it's not new, hooray, welcome to the club. If it is new, hooray, welcome to the club. It's just that this is how we're going to be doing stuff. So this little tiny study guide that you have. There's a couple more copies up here if you need another copy. I remembered to put it online. It's online if you need another copy. You can put as many notes as you'd like on here. You could bring your notebooks. You could bring everything. Let's open everything. Good. We still have one more class before our exam on Monday afternoon. We do have class Monday at this time. On Friday, we were talking about using what we know about electronic circuits to ask specific questions, and I'm going to use reserved words, analyze a specific system. So right there on the top, next to our fantastic ISBT logo, is ISBT111 Technology and Systems Analysis. Okay, so us sitting down and looking at an electronic system and then taking a hard look at the pieces inside the box. That's analysis versus synthesis. Systems analysis is sort of odd to see those two numbers together, or two values together. It's sort of like sweet and sour. Everybody likes Sour Patch Kids. They're sort of sweet and they're sour. Right? They're sour first, right? And then they're sweet. They're sour first and they're sweet. So systems and analysis, or a systems thinking and an analytic thinking, as we've talked about, are not opposites. They're complements. There's this idea of the art and the science. So before we keep on going, I'm going to put this goofy little picture up here again. We had art on this axis, and we had science on this axis, and then we had different on this axis. Usually the artists are charged with finding differences in situations, and the scientists are charged with finding same in situation. They're not, one's not better than the other. They're both useful and for solving problems and for defining problems and for innovating. They're both needed at the same time. We talked about problem formulation, telling us what is the problem, and up here in this corner we had problem solving. And then we said if you're down here, you're just sort of doing your job. It's not a bad place to be. It just happens to be where you're doing your job. You're not spending all day researching, being a scientist. You're not spending all day being amazingly creative. You're just doing life. You're just doing the do. Down here, you're being amazingly creative. Up here, you're being very amazingly analytical and scientific. And if you do both, we like to define the word innovative. So that's our guide. So I'll just put that back out there. We talked about these two circuits on Wednesday. Does that mean you need a copy of these sheets? We good? Any copies? Wonderful. We talked about the first circuit. It was battery with a resistor. It had 10 volts. It had a total current. It had resistor 1, and the resistor 1 was 15,000 ohms. And then we analyzed it. We said, what are the parts? While this thing is running, what sort of things can we talk about? And it specifically asked us, well, if we're talking about V equals IR, we know the V, we know the R, can you find the I? That was easy enough, okay? And we talked about the I total coming out of here was a total circuit, and we found out what I total was, and that allowed us to use this I total equals V total over R total. Good? Review? Fantastic. We then looked at the second one, which was very similar. It wasn't the same, but it was similar, but it was kind of different. It had a second resistor. So we got this guy. Back and forth, it was still 10 volts, that's the same. Still had an I total, that was the same, but now it had an R1 and an R2. This guy happened to be 12,000 ohms, and this guy happened to be 24,000 ohms. We found the total current. We even found the current through resistor 1 and the current through resistor 2, which was the same. It was all the total current. But then we went back and we specifically solved for these voltages. What was the voltage between here, V, A to B? I guess I should label that, A and B and C. And then we found the voltage V, B to C. And then we found the voltage V, A to C. Okay? And we used the equation to sort of solve that. Now that we know, we've already seen the answer if you went ahead and calculated it on Wednesday. And this happens to be the same answer we had before. We calculated, we said, you know what, if you look at this situation, the voltage between A and C is actually the same voltage between this guy and this guy on the battery, right? I know it's a review, but... So we said this guy was 10 volts. Does everybody see that? I don't want to just convince you, but everybody sees that. The drop from the top of the circuit to the bottom of the circuit on this side in front of the the resistors is the same as the drop of the top and the bottom on this side, because the only thing that connects this side with that side are wires and not resistors. If you have your sheet from Wednesday, that's fantastic. If you remember, you guys remember what those voltages were? That top voltage drop from A to B and the bottom voltage drop from B to C? Do you remember?
3.33.
The first one was 3.33?
Yeah.
3.33 volts from there.
6.66.
6.66 from there.
That's our thing.
Okay, that was our guy?
Yeah.
So yeah, if you remember this, if you had a picture of this in your head from Wednesday, it's the same problem we had on Wednesday, obviously. But what I wanted to do was step back and look at that. We mentioned earlier that 3.33 plus 6.66 with some round-off error is 10. Okay, that's where the voltage came from. If the total drop is 10, then the voltage drop across one of the resistors happens to be 3.33, then the rest of the voltage, bless you, has to appear here. Or if we solve this first and get 6.66, then this guy has to be 3.33. But what I want to do is I want to do something scientific and do something sane. I want to look at the ratio between this voltage and this voltage and this resistor and this resistor. Okay. What's the ratio between 3.33 and 6.66? That's the result, sorry. Is it half? 1 to 2? If this guy is 1 3.33, this is 2 3.33s, right? Does that work? 1 to 2. What's the ratio of these voltages, these resistances? 12,000 ohms to 24,000 ohms.
Wow.
It's also Dan half. Okay? 1 to 2. Okay? That's a scientific discovery. That's the same thing. We went through a lot of equations on Wednesday. I'm not asking you to just see it. But given this situation, if you're told that there's a resistor 1 in series with a resistor 2, then the ratio of the drops is the same as the ratio of the resistances. Okay? That's the same for every series resistance. Not trying to learn anything new. We're just trying to use this idea over here. Yeah, I know it's different, and we saw this new thing, but hey, I wonder if that's something I can sort of tuck away. Okay. 3.33 and 6.66. I know this guy. Good morning, sir. I know this guy is 1.5. What is this ratio relative to 10? What's 3.33 relative to 10? How much of the 10 is going through the first resistor?
Third.
A third. I like that. 1 over 3. And to just finish the conversation, how much of the voltage is falling across the other thirds, right? 2/3. Okay. So the total voltage was 10 volts. 1/3 of the voltage is going across R1. 2/3 of the voltage is going across R2. What about that analysis over here as opposed to the total resistance? We already know that R total equals 12,000 plus 24,000. That's 36,000. What's the ratio of this guy to the total resistance? 12K over 36K and 24K over 36K. What's the ratio of those resistors? What's 12 to 36?
30.
Thank you. And how about 24 to 36? Ooh, write it upside down, right? There's so many different ways to analyze this system, and all the numbers are they sort of give you this gut feeling. We haven't done any calculations yet other than looking at ratios. But this is the same thing each time. Not asking anybody to see it this way, but just to realize that that's what scientists do, okay? They recognize that the situation is different, but they look for some sort of general conclusions I can make. The voltage across this guy to this guy, okay, is the same 1/3 as the resistance of this guy to the total resistance. And to say that, the scientists say, oh, by the way, if you want the voltage across resistor 1, then just take the voltage across the total resistances and multiply that by the ratio of R1 to the R total, and do that all the time. Well, that's our equation that we have. That's our equation for the voltage divider equation. So that is an observation that scientists made a while back and said, hey, we've tested our hypothesis, that's always true. It's the same story every time you find two resistors in series. The ratio between these resistances happens to be the same ratio between the voltages. How do I do that? That's this guy, right? Voltage across R1 to the voltage across all of them is R1 to R total. That's this equation with the written as ratio equals ratio. Okay? Not ask anybody to memorize it, just appreciate it. All right, let's turn the page and go to the back. Another circuit. Two resistors, they're the same. This is 10 volts, that's the same. There's current flowing, that's the same. This is called I total. This guy is R1. This guy is R2. Just to make things amazingly different, R1 equals 3 kiloohms. R2 equals 9 kiloohms. Okay? I see a lot of differences here. Please tell us the values of I total, I1, and I2. That's what they were asking for. There's I total. Where will I find the, well, it's on here, right? I1 is here. Here comes I total. It comes this way, and then it splits. I1 goes through resistor 1, and then I2 goes through resistor 2. And then what happens down here? Sort of like a garden hose that splits, they all join back up again. It's current. You can split the current, and then it comes back together again when you're done. So it's I total at the top, and it's I total at the bottom. They're the same I totals. We need to find out what the current is, I total. Well, we can just look at it again. Maybe, well, it's different, right? You guys already know this, right? What's different specifically about those two resistors versus these two resistors? What's the big major difference?
Parallel.
They're parallel versus series, yeah. So this is a parallel issue. That's a series, and that means something. They really are different. Because they really are different, then parallel circuits share the same features, but they don't share the same features as a series circuit. Okay, so we have to observe that they're different first, and then we can go ahead and say, oh, we need tools for the parallel circuit. But regardless of whether they're parallel or series, this equation still works. The total voltage equals the total current times the total resistance. Okay? V equals IR always works. Ohm's law works whether you're series or parallel. So let's just do it that way. I total equals V total over R total. Excellent. I need the total voltage. Anybody give me the total voltage across that circuit?
10.
Where'd you get 10 from? Alright, so it's right there, right? 10 volts. I need the total resistance. 12K or 12,000, right? I don't want to put K there because K is an engineering concept. I should put 12.
Is that the total resistance though?
12,000 ohms. Wait a minute, I'm hearing some differences. I'm hearing some differences of opinions.
Isn't it 1/3?
Everybody's right. I love it. Yeah, sure.
1 over the resistances and then multiply it by the -1 with the sum.
Remember, we have to use the adding together resistances in parallel uses a different equation than adding together in series. Okay? Adding together in series, just that. Add them up. Okay? This guy may be not that. Although I absolutely love and appreciate your answer. But something's different. Okay? It's different this time. We need to use the equation that you use when you have two resistors or several resistors in parallel. And that's the one on our equation sheet that says the R total for those things that are in parallel. That's not on 11. Sometimes we say resistors parallel. We use the parallel line thing. It's that guy where you add them up. 1 over R1 plus 1 over R2. And then when you're done, don't take the square root of the damn thing. Take a 1 over the damn thing. That one. Okay? That's the equation. It's different because the resistors are laid out differently. However, it's the same for all parallel circuits. Again, going back and forth, we're going to use this equation. We're going to add them together in the 1/overs. Once we get them, we're going to switch them back on the other side again. So we need to literally add 1 over 3,000 plus 1 over 9,000. Okay. And then when we're done, we need to take the 1 over that guy. Anybody want to punch that for me?
Yeah, it's 2,250.
2,250 ohms. Is that a nice number? Is that your favorite number? 2,250? What if we didn't use a calculator and we were back in, when did we do fractions? 5th grade? 4th grade? I wasn't a very strong math student, so I forget when I did it. It was probably high school by the time I got fractions done. 1 over 3,000 plus 1 over 9,000. Anybody remember the rules of adding fractions?
They have to be the same.
Thank you.
Same top.
Same bottom.
Same
They have to have the same denominator, right?
That's right.
Okay. So how can I turn 1 3,000s into a fraction that is something 9,000s?
Common denominator.
I can multiply it by 3. It is a third, right? So 1 over 3,000. If I multiply that by 3 over 3, I get 3 9,000s. Can I just randomly multiply stuff in math? Sometimes. Can I just randomly just pick something? Guess what? You're getting multiplied by 3 over 3.
You gotta do it to the other side.
Do I have to do it to the other side too?
I'd rather do this.
Isn't math fun? Why can't I randomly multiply this number by 3 over 3? That sounds like it's breaking a lot of rules. Picking a number and multiply it because I think I need it. What's 3 over 3? Are you allowed to randomly multiply numbers by 1? Sometimes. Yeah, it turns out when it comes to multiplication, you can multiply numbers by 1 as many times as you like. Because it just so happens you get the same number back. Right? So 25, I'm going to multiply that by 1. Go ahead, and when you're done, come back and tell me the answer. It's 25. I'm going to multiply by 1 again. It's still 25. Okay. The only reason we're allowed to do this is because we're multiplying it by a fraction that evaluates to 1. Okay, now we can do 3 9,000s plus 1 9,000 equals 4 9,000s. Oh my gosh. And then we have to invert that back over again. Does anybody have, is anybody's favorite fraction 4 over 9,000? Anyway, the answer is 2,250. It just happens to be the answer, okay? It's telling us where we got it from. Alright. Our total resistance from here is 2,250 ohms. Well, that's different. Okay. That's kind of crazy. The total resistance is 2250. Resistor 1 was 3,000. Resistor 2 was 9,000. The total resistance is smaller than any one of the other resistors. Are we happy with that, or are we sad with that? The overall resistance of these guys in parallel, the overall resistance of 2250 is smaller than 3,000 and 9,000. The whole system together is smaller than any one of its parts. Is that surprising? Is it shocking? So if we happen to have a line at Walmart and it takes 3 minutes to get through this line, and then it takes 9 minutes to get through this line, but some people choose this direction, and sometimes the overall is 2.2 minutes. It turns out that this is another same thing. When we add additional lanes in parallel, it doesn't have to be just 2. You can do it for, this works for 3 parallels. You can open, if you're at Walmart, you can open up 33 checkout lanes if you'd like. You can have as many things in parallel as you like. The more resistors you have in parallel, the total resistance for the system is smaller than any one of those. But it's for the system. Because while you're over here stuck in this line, which is 9,000, these guys over here are doing 3 times as many. It's only 3,000, but overall, if you go ahead and do it, 4 people made it through the line as opposed to just 1. My brain's going to explode. When we're talking about series, whenever we add resistors in series, the resistance always goes up. The total resistance always goes up. When we add resistors in parallel, the total resistance always goes down. It always goes down from any one of the resistances. And that's the same for checkout lines at Walmart and exit ramps off a highway or parallel executions. How many people have, well, you have like a 16-core processor in your phone, right? Yeah.
17.
Yes, I do. 17 core processor. So the reason why his processor has 17 cores is because it can do 17 things at the same time. So it can calculate in parallel 17 times as fast as any one of them. That's pretty cool. Okay, that's parallel. So we're back. Here's our answer. The total current is 10 volts divided by 2,250. Anybody want to help me out with that calculation? Here, did you already do that? 10,000 over this total resistance.
Wait, what is it?
It's 10 volts over 2,250. It's some goofy number.
It is
not gonna be
0.00.
0. What?
0.004. 4 milliamps.
There you go. So amps, which is the same as 4 milliamps. Okay. Oh my gosh,
What?
4 milliamps. That was a 4 there. Oh, my brain's gonna explode. It all sort of makes sense. Now they want to know what is the, so we got 4 milliamps to this circuit. Okay. They want to know what is the current that goes through resistor 1 and what is the current that goes through resistor 2. Okay. We need to figure out, we need an equation for that. Yes.
You do compute
Same.
the voltage.
I love that. Okay, you get an A for the day. It's the same thing. I'm sorry.
Voltage divided by a resistor.
So this time around we're talking about splitting the current instead of splitting the voltage. So instead of having a voltage divider equation, we're going to use the current divider equation. That's what makes it. So this is the current for the resistor we're worried about, the I1, equals the total resistance. I'm sorry, I'm still over there. The total current, and then we're back to this ratio thing again. Okay, we need to put the resistor we're worried about over the total resistance in parallel. What do I have here? I have the total resistance in parallel divided by resistor 1. In this equation, we had resistor 1 divided by, so it's upside down, right? It's inverted. First of all, everything about this problem is inverted. These guys were inverted, this guy was inverted, these guys were inverted, these guys are inverted, okay? Just looking at it, learning at it from a scientific way, why do you think this equation has this ratio inverted? Why do we put the total resistance in the numerator and the resistance of one of the resistors in the denominator? Because it says so, right? Why did we do that in the first place? Over here, we take the resistance of one of them and then divide it by the total resistance. Does that get us a small ratio or a large ratio? Smaller than 1 or larger than 1? When we take a part and divide it by something bigger. Take a hint here. It's the same, damn it. No, it makes it smaller, okay? We take a part, which is only 12, and we divide it by the total, which is 36, and we get a number smaller than 1. We get a fraction of the total. So that allows us to calculate what fraction of the voltage drops from here to here. How about this guy? What if we take the total resistance in parallel, 2,250, and divide it by 3,000? $2,250 divided by 3,000. What happens to this ratio? Is it less than 1 or bigger than 1?
Less. 0.75.
Is it 0.75? Somebody punch it through. Is it? 2,250 divided by.
I was right.
Is it 0.75?
I hate when he's.
It's 3/4. Look at that. Times the total current, which was 4 milliamps. What is 3/4 of 4? If I give you 4 cookies, and then I ask you to give me 3 of those 4 back. 3, damn it! It's 3. 3 milliamps, okay? 4 milliamps is coming through here. 4 milliamps. 3 milliamps is going through resistor 1. Before you get out your calculator, how many milliamps are going through resistor 2? 27. 803. None. 4 milliamps, they split. Some of the milliamps went this way, 3 of them did. And then the rest went this way. How much is going through here?
I get really confused actually.
Oh, because there's 4. Oh, we're running into it. I didn't see the 4 right there.
It's all good. It's all good. Our total current was 4 units of milliamps. 3 units of milliamps went that way, leaving 1 left to go this way. You don't need to reason it out and use fifth grade ratios, you can calculate the damn thing if you'd like. The total current going through resistor 2 equals the total current, which was 4 milliamps, times the total resistance, 2,250, over the resistor we're worried about, which is 9,000. Anybody know what that answer is? Look at that! How'd that work? Oh, I don't know. I know I have a bunch of numbers up here. The ratio of 3 milliamps going this direction versus 4 milliamps total. What's the ratio of this resistor to that resistor when it comes to resistance? One of them is 3 and one of them is 9. Now we're back to that question. You remember when you gave me 12 before? Right? 3. That's 1/4. 9 out of 12. That's 3/4. But remember, resistor 1 is 1/4 of the total resistance, but 3/4 of the current. It's the inverse. My head's going to explode. It's 1/4 the resistance, but it gets 3/4 the current. That makes sense. This is less resistance, right? If you're the checkout person at Walmart, and this happens to be the fast 20 items or less lane, and it only takes 3 minutes to get through this lane, you're going to get more customers. If this happens to be another lane over here that takes 9 minutes because you have as many items as you'd like, it's going to have a fewer number of customers. For every 3 customers through lane 1, you're only going to get 1 customer through lane 2. Okay? So your answer of 12 very early on was the right answer, as long as you inverted it. My head's going to explode. Everything over here about parallel is the 1/over argument. Okay? This guy is 1/4 the total resistance, but it gets 3/4 of the flow because it's the other part. So if you take a pie and you slice it into fourths, and you say, here's 1/4, and the rest is 3/4, 1/4 of the resistance, 1/4 of away, leaves you with 3/4 of current. Craziness. That happens all the time. It's the same. If it was your job to be an electronics engineer, and you had to spend all day staring at series circuits and parallel circuits, hopefully it doesn't happen because you're a robot and it's like, oh my god. The same thing happens all the time. Okay? And after a while you don't need your calculator because you just sort of look at it and say, oh, well, I understand what the ratios of these guys. I'm not going to ask you to do that on the exam. I just want you to appreciate that the numbers don't come from just out of thin air. Hopefully they sort of make sense. Cool. I want to set this up just to totally mess with your minds on Friday. Oh, that's right. Oh my gosh, what fantastically awesome graffiti on the board. Am I trying to erase it all? Ben, is our board just as awesome as the P chemists?
It's better.
It's even better. Look. Thank you for that. Race. My arm's getting tired. I can't do it. In addition to playing with electronics, different. Those two basic things, resistors in series and resistors in parallel, we're going to see those patterns everywhere in the universe. We'll never leave it again. It's not just electronics. We're going to see it at Walmart. We're going to see it in computer science. We're going to see it in business. We're going to see it in everything. Parallel and series is one of those very fundamental concepts, like counting to 10. That's a very fundamental concept. And then you see numbers. I see numbers everywhere because counting to 10 is very fundamental. Let's look at this guy. Another circuit. It has components that are the same as the ones that we saw, and it has components that are different. 10 volts, that looks the same. Total current, that looks the same. Resistor 1, resistor 2, resistor 3, resistor 4. 4 resistors, you've got to be kidding me. Okay? Each of the resistors has its own resistance. 1, 2, 3, 4. 1,000 ohms, 2,000 ohms, 3,000 ohms, 4,000 ohms. Well, that was convenient. Thank you to the person who wrote this, because the name of the resistor is the same as the value of the resistor. Because I didn't want to memorize it any other way. We came back to just welcome the 7th gate of hell.
Oh, this is cake.
Cake it is. 10 volts is the same. I total's the same. There are resistors, that's the same. What's different about this one? One of these things is not like the others.
Series. They all run parallel.
It's a series parallel circuit.
What? What kind of nonsense is that? A series parallel. We've learned about series. We've learned about parallel. This is a series parallel circuit? Is that legal?
Mm-hmm.
Can you do that?
You gotta do that.
What kind of rules are we going to use? What kind of equations are we going to use? Do we need a whole new toolkit for series parallel tools? How can we solve it? It's different, right? What do you mean same? No, it's different, right? No, it tastes great. No, less filling. No, it's better. No, it's away. It's different, but it's the same. There you go. But it's the same. It is a parallel circuit in series with another resistor.
You just gotta simplify it and it's easy.
How do you want to simplify it? How do you want to make it similar to a problem we've solved before?
Make the parallel circuit, the parallel R1, R2, and R3.
Yeah.
Into an R equivalent, which would then in turn make it into a series circuit.
So if we said this really is just an equivalent resistor, you can call it whatever you want. We can call it R EQ for equivalent.
Yeah.
We could call it R parallel. We could call it R plus 2 plus 3, whatever you want to call it. Okay. We could say, hey, wait a minute. What if resistors 1, 2, and 3 act like a word that starts with an S? I'm playing Scrabble. A system. Thank you. More coffee for you. You get coffee. If we take the parts and turn it into a system and then treat them as a system, this is cake. All of a sudden, it stops being a hybrid parallel series problem and it just turns into problem number 2. It's just a series problem. We need to find out this R equivalent. What is the total resistance of resistor 1? What equation would I use? Just add them up? What do we do?
Yeah.
No.
It would be the
1 over.
1 over.
I have, sure, just add them up. And then I have the 1 over, folks. So just go to war until arm wrestle, maybe?
For the parallel,
For the parallel, what equation should we use for this guy?
the regular parallel,
What is the parallel?
which would be over 1.
It's the 1 over crap, right? We need an equation. So we need to go, the resistance for the parallel, you can call it EQ, you can call it the parallel equation, is 1 over R1 plus 1 over R2 plus 1 over R3. And then when you're done, put it that way. All right, here we go. 1 over 1,000 plus 1 over 2,000, plus 1 over 3,000. You can choose to use a calculator. The calculator app on your cell phone,
545.
or you could go ahead and go back to 5th grade and find common denominators. Or we're just going to say how much?
545.
545 ohms. All right. Together as a system, this is 545 ohms. This guy is 545 ohms. The overall resistance of this guy is smaller than any one of these guys. Are we happy with that or sad with that? Did we make a mistake? The overall system, total system resistance is smaller than any one of the individual paths. We happy? We're happy. We like that. It's how parallel circuits work. Okay? If we know this guy is 245, and we know this guy is 4,000, what's our total resistance for the circuit? I know, sorry. 4, 5, 4, 5. Is it the world's craziest coincidence that the number's 4, 5, 4, 5? No, not really. There's a reason, but it's nice to draw. 4, 5, 4, 5, 4, 5. With that, we have run out of lovely time on a Friday. And now it just turned into a series circuit problem, which we did before. This is what science does. Science looks at a problem, sees that it's different, sort of manipulates it into something we've seen before, and then just says, well, now we know how to solve that. That's no problem. We'll simplify it by solving this. So anyway, have a lovely weekend. We'll be back here on Monday. We do have class on Monday. This time, we'll finish up this problem. We'll talk a little bit more about concepts leading to the exam, and then we'll have the exam in the afternoon. We'll finish up. We'll have some more fun on Wednesday and Friday of next week, and then, I don't know if you guys heard, but after Friday of next week, spring is here. Yeah! Get out of town! And for the freshmen, this is your first official spring break. So happy for you. Yeah, rock on! Thanks, guys.
Thank you.